So, I have some time and thought that this subject on threading and benchmarks would be helpful. If you think it is actually helpful, consider leaving a like. But first I want to say that these videos I'm making are about what you want to see. If there's any subjects that you'd like me to cover, leave a comment. Until then, I'll continue making random videos about whatever. On to coding. First we need to create the algorithm where we actually need to create a project first. So I'm making this in C#, but it applies to other languages as well. And I've implemented a thread manager in both Python and C++, as well as C#. And this code is available on GitHub with the link in the description. So creating the algorithm for prime numbers is just a basic for loop that goes through the numbers that we want to check. This check also loops through the numbers that are smaller than the number we want to check for prime, with each of those numbers being divided into the number we're checking, and we check that division to see if its remainder is 0, which apparently I can't figure out. It takes me a little while to remember how mod works. This % symbol, apparently, I write in too many different languages. So if it returns 0, then we know that it's divisible by that number. And so we mark it as not prime. It's also good to use a reference so that we can validate the process to ensure that these results that it's generating is actually correct. But right now I'm just checking it by eye, and I'll automate it a little later. And so I finally figure out how to use mod. I was thinking it returned the decimal value as opposed to the remainder, but anyway, don't use it often enough. But now that it's working, I need to slow down the results so I can actually see what it's outputting. And I keep the slowdown, I keep it the same through the benchmarking to maintain consistency. It doesn't matter if it's there or not, just I don't change it after the first benchmark. And it looks like the validation is correct, but they leave out 0 and 1. Now that the algorithm is working, we want to benchmark what we've created. It's as simple as capturing the time before the execution and capturing the time after the execution, then taking the difference, which gives you the duration. Write down the duration to keep track of our changes to the code and how that affects the performance. But before we jump into creating threads, we want to optimize the algorithm first to the best of our ability. With this algorithm, we can remove evens because an even number is always divisible by 2, and then running a check after every change to ensure that it is still producing correct results. The next big change to the algorithm is only check half the numbers below the suspected prime number, cutting the workload in half, because if you multiply half the given number by 2, anything bigger than 2 multiplied by half will produce a result bigger than the number we're checking. So it's obviously going to be smaller than half. I do want to check the half value itself though, and so I use ceiling to ensure that I get the end count for the loop is 1 larger than half. But this ceiling function is computationally intensive, or at least that's what it seems like from the benchmarking. But what should have produced a faster result ended up producing a slower result. I removed the ceiling function to see if it was causing the problem, but it actually didn't change much. Then I move the half function out of the for loop to see if it was computing it every time through the loop, and that didn't change much either. So with that, I add a break out of the for loop. Once it determines that the number is not prime, there is no purpose in checking other divisors, which didn't change the performance much, but it did make it a little slower. Now, this being a small test with very small changes in the time it takes to compute, increasing this a million-fold will show larger discrepancies. But I want to actually validate before moving forward with the next crazy changes, just to make sure that the algorithm is maintaining accuracy. Once I figure out how to initialize an array and figure out how to check that array against another array, we can move on to the next step. I write in too many different languages. I jumble them up sometimes. And it doesn't pass validation because I include one, but I don't have two. These both being a special case where a prime is defined as only divisible by 1 in itself. And I created the cheat for the divisible by 2 line. This removes 2 from the results. One of the downsides of optimizations is that you may create errors for edge cases. Always test your code. We don't want to validate when we are running these larger tests because it's just too much data to be checking against, and the table isn't that big. But it seems to be outputting a lot of results compared to what I remember when I wrote the algo like 20 years ago. So Googling a distribution curve does show a lot of numbers early on. So I'm guessing it's correct. Honestly, it's not the purpose of this video is to make a proper prime algorithm, so they exist out there. So it takes 5 minutes to run 2 million and labeling results, so I know what they are as we keep moving forward. On to implementing recursion. We need to exhaust all optimization options before we go on to threading. I don't particularly like when a function has multiple returns, but it needs to break the execution. And I don't feel like making a complicated if statement. We're not making a prime function, we're showing threading and benchmarking. That's the focus. I removed the linear execution and replaced it with recursion, but I should have kept it because I ended up rewriting it anyway. And I needed to be able to switch between the two for testing. But we need to validate this change to ensure it still works, and that's really fast compared to the linear equation. And with 2 million, it's still really fast. Now you may say, why do we need threading? But before we get into that, I need to recreate what I deleted. So in single threaded mode, you can see the CPU usage, and it's 100% for one of the CPUs. In case you're not sure how to get here, this is Task Manager, and if you right click the graph, you can choose overall or logical, where logical will show you each individual CPU. With C# and .NET, they provide a nice feature called parallel for loop. This makes threading easy if it's just a for loop. Just need to convert it over to the style it uses and add a lock on the prime boolean. Locks are to ensure that only one thread is writing to that variable at a time so that they don't step on each other. And it needs an object instead of a struct for the lock variable. So now it's using all CPUs and maxing them out to 100%. But it's still not faster than the recursive approach. So why would I do threading if it's not faster? Well, this is a contrived example. So in many cases you will see that threads may provide a performance gain, and in some cases you may not see a performance gain. But this is more about the process of how to determine which approach you should take for a given algorithm as opposed to optimizing the prime number search. It even took longer than the linear approach. Oh, it was because I wasn't breaking out of the for loop. Now it's faster. Can we make recursion faster with threading? And I can't code. It is faster than threading with a linear approach, but it still isn't faster than no threads with recursion. What if we increase the number of primes that we want to search? And we run into an error. Now we have to take a different approach because the recursion cannot execute that many number of times due to the limitation on how deep the stack can go, i.e. how many times is prime function calling itself. And that's why we get the stack overflow error. Okay, so back to the threaded approach. See these huge dips in the CPU performance? That's called thread thrashing. But for some reason, the parallel for loop seems to smooth it out. That's good if your algorithm can conform to just a for loop. But what if you are creating threads throughout your application? Or you're coding in a language that doesn't have a parallel for loop? There's a nice article on thread thrashing if you would like to read it. But thread thrashing is basically the CPU switching between all the threads, trying to give them equal time to do work. But the more threads you have, the less time the CPU can give them to do work. Due to the simplistic nature to this algorithm, I need to get creative so that I can emphasize thread thrashing. So I'm converting the parallel for loop over to a pure threads implementation, then starting them all at the same time. They have all these nice features for tasks and threading, but they don't have a start all function. Then I spent way too much time trying to find out where I'm missing a bracket, only to discover that I have an extra bracket. I'm not missing one. Well, it's actually a parentheses. And away we go. First it needs to create all the threads, which doesn't seem to have much CPU usage. Then it starts all those threads, and we run out of memory. So I switch over to 64-bit executable, which gives me more memory. Back in Task Manager, if you switch over to details, it's best to enable the columns, threads, and handles, which help you see what your threads are doing. Handles are the handles to each thread, which you can run out of. And we're using a lot of memory creating these threads. And it looks like it is caching to disk. But we ran out of memory again, so I'm doing a quick check as to how many we are able to create before it crashed. This can be mitigated, obviously, but I'm trying to create a contrived example to emphasize thread thrashing. Now we have a result. For some reason it's only using half the CPUs. Not sure why that is. This isn't an Intel CPU with hyper-threading, so not sure what's going on. But you can see more thread thrashing as it tries to max out the CPUs. The telltale sign of thread thrashing is that the CPU usage starts out high, but progressively drops off in CPU usage while there's still a ton of threads doing work. Eventually, as the threads complete, the remaining threads get enough CPU time and start using more of the CPU. So how do we go about managing thread thrashing? By using a thread manager. With a thread manager, you can control how many threads are executing at the same time. This allows the thread to maximize CPU usage, at the same time having the most amount of threads running in parallel without taxing the CPU. The one I implemented, where the code is in the GitHub repo with the link in the description, it uses 3 queues. The first is the waiting to be executed queue, so that the main program can create as many threads as it wants while still doing other things. The second queue is the actively running threads, and the third queue is the finished threads. That third queue is important. The thread manager needs to join those threads back into the main program and properly release resources, i.e. the handles that were created, those need to be disposed of. This keeps memory usage down and keeps your program from crashing. The other 2 aspects are max requested threads. This is a hard set parameter by the coder. This allows you to say that you don't want any more than X number of threads running. You may want it to only use half the CPU for some reason. The next one is CPU usage. The manager monitors CPU usage and makes sure that CPU usage stays below 80%. I use 80% because when you let it go to 100%, the system can become non-responsive. So the manager will check and will not start new threads until the CPU usage drops below 80%, or whatever the designated value is. Here's a quick scroll through the thread manager code. It also prints out debugging info, how many queued threads, how many active threads, how many completed threads, which helps greatly in trying to find any issues with your code. Okay, so let's create the code that uses the thread manager, which I start off on the wrong foot. Run threads is an internal function I should be calling start, and I should make run threads a private function. Second, I try to set max threads to 0, so it doesn't start the threads until I add them, but there seems to be a bug with that, so I need to create the max threads before I start the thread manager. Oh, and since this is a contrived example, I need a lot more processing in the thread loop. So I run it 3 times to increase processing. Okay, so with thread manager managing the threads, there's this weird spiking pattern, most likely due to the algorithm not being computationally intensive, but it is able to maintain a heavy load against the CPU despite that lack of CPU computation. And you can see how many threads are being completed per cycle with the debug messages, but bucketing is actually better, so let's go on to that. Since this algorithm doesn't actually have a lot of processing and I didn't think about it while I was coding this, only when I was editing the video. Bucketing can also be another approach, where you create a bucket, say numbers 1 through 100, then 100 to 200, and so on. Then each thread would be processing 100 primes each instead of just one. So here's me breaking it into buckets, and with that, all the CPUs are at 100%. So there you go. How to optimize your code using various techniques depending upon how it's implemented. If you like this video, consider clicking the like button. If you found it useful, consider donating. And if you want to see more, consider subscribing. Thanks for watching. Until next time.